280, 360 million years ago.
Say something.
Something.
Okay guys, I'm going to go over some of the laws of thermodynamics. We're going to talk about what they mean and how to apply them, generally speaking. So let's look at thermodynamics. We know that thermodynamics, based on what we've been doing, is talking about heat transfer. Heat transfer is usually when things have difference in temperatures. They have differences in average kinetic energy. So they will have their particles run into each other and exchange energy, almost like the little collisions in Newton's cradles, right? Like those little Newton's cradles. So if we do, let's see. So remember, like the Newton's cradle. If I take this guy, slam these two orbs together, they'll transfer some of their kinetic energy into one another, depending on what they're doing, right? If they're different masses, they'll have different outcomes of velocities and things like that. And thermodynamics explains why things like hot to cold works the way it does, right? And it has to do with entropy. It has to do with the second law of thermodynamics. We'll talk about that in just a second. All right. So when energy is transferred across system boundaries, it's going to be seen as either work or as heat, okay? That's added or lost from the system. Okay. First law of thermodynamics, sorry, this is kind of all jumbled up, but it's okay. Whenever heat is added to a system, there's an equal amount of some other form of energy, okay? So when you add heat to a system, it either increases the internal energy, and we know internal energy is U, or change in U is the change in internal energy. And this is the equation for it, by the way. This is the Q plus the work, right? Now keep in mind that if we're talking about heat leaving a system, which is Q, if heat leaves a system, it's going to be negative. If heat is added to the system, it's positive change. Same thing as if you do work to the system. If work is being done to the system, it would be a plus, right? So imagine you have like a gas or something like that, like in a balloon, like an air balloon, and you compress that thing down, you squeeze it together. It's going to end up being positive work done to the system. So it's very hard to kind of remember that, because we think of work as things like you pushing stuff around. We're talking about work done to the system. In this case, we're talking about gases most of the time. If work is leaving the system, so if like that balloon expands, right? If the balloon expands and becomes bigger, it'll push the outside system, so we would call that negative work, okay? So just keep in mind that your vectors matter for this, just so that we can accurately calculate the change in internal energy. All right, so the change in the internal energy of a system is equal to the heat or plus the work done on the system. And just keep in mind that it can be positive, negative, right? So, and then here's a picture of the Big Bang. Really, really close-up things. And then over time, entropy increases. We end up getting a lot of spreading out of that energy. You see these things are kind of all close together at the beginning, and then they end up spreading out into space and time to try to make everything equal over long periods of time. All right. So the temperature and the first law of thermodynamics. Remember, temperature is the average kinetic energy. It is not heat. Remember that this is not the same thing as heat. So this is not heat. Okay, not equal to Q. Sorry, that's kind of like a sideways equal sign. All right. We can generally say that temperature is energy that works great for gases. Okay, so we can usually relate temperature directly to whatever's happening with heat and work and things like that. So we can kind of look at that. Where do we get energy from? It's work done to the system or heat added to the system. Therefore, we get this equation. So here's the equation I was talking about. All right, the ideal gas law, this is from chemistry. PV equals nRT, or the Pivnert law. So what we're going to be doing here is we're going to take our pervert law, PV equals N, which is the number of moles in the system or number of particles. Rate is like a gas rate, the rate of expansion for a certain ideal gas or something. So this is the ideal gas law. So what we're going to do here is we are going to actually look at the relationship between temperature, pressure, kind of from some of our other laws, Charles and Boyle's law, and we are going to take this and work under the assumption that we are keeping the gas particles trapped. Okay, we're not letting anything escape. So we end up with an equation that looks like this. So we're not really going to be quantifying. So we're not going to be coming up with exact numbers for temperature based on pressure and volume, but what we are going to be doing is doing qualitative statements and proportional statements, right? Proportional, sorry. Sorry, I can't spell. So we're going to be doing like proportional analysis, which is what we've done with gravity and work and energy, right? So we kind of see like if I change this much, what's going to happen to the rest of it? So you can see basically we're going to really not worry about this guy down here, and we're just going to say that PV is equal to T in terms of relationships. Okay, so that's how they're related. They're all directly related to each other. If I increase the pressure, the temperature goes up. If I increase the volume, the temperature would go up. Or this is the change in volume rather. If I change the volume, that would be caused by an increase in temperature, okay, because it makes the particles spread out, okay? All right. Since we investigate trapped gases, we simplify it. So this is what I was saying here. This is why we can eliminate this bottom part, because we are trapping the gases, so we're never going to have a change in the number of moles. All right. So what does it do to a gas? So energy and temperature, work and heat. These are some equations you need to know. Work can be substituted right here. If I press a gas, I'm going to change the volume. So if I decrease this right here, it's work done to the system. So this can also be written sometimes as negative P change in V. Negative P change in V. Because if I do work to the system, what's going to happen to this volume here? If I press a gas down, if I compress it, right? If I have like a spring and I press it downward, the change in distance, right? Let's say it ends up doing this now. So now it's been coiled downward. So I lost a little bit of height. So the change in my distance was negative, right? The same thing's going to happen to a gas. If you imagine that this instead of a spring was a gas, changing the volume would be pressing it downward. So you'd actually have a negative change in volume, but that would be positive work done on the system, right? Now, so that's kind of interesting to think about. So if you don't put this negative in there, you have to understand that the gas is the system. So by pressing it down, it's positive work added to the system. Positive work added to the system. If the gas expands, it's work done to the outside of the system. So it's it really just depends. All right, so this is the important stuff right here that you need to know. How to read these pressure volume graphs. So you can see on the y-axis we got pressure. So you can see the pressure is not an actual number, but it's like a multiplier, right? And on the bottom we got volume. So again, not an actual number, but these are kind of like proportional amounts. And we remember from our last slide that temperature is the combination or the relationship of pressure and volume multiplied, right? So it's a direct relationship. We can also calculate work this way too, by doing pressure and the change in volume. Okay, so these are related to this graph. You could calculate pressure and temperature But for work, we have to kind of do a change in volume. So we're not going to really be able to do it with just this graph right now. But we could look at which temperature is going to be the greatest, right? So we would take, so for point A, 5 units of pressure. 5 units of pressure would get plugged in here. 3 units of volume. So what's 5 times 3? This would be 15 units of temperature, right? We don't know quite what that would be, but it would be 15 units, right? All you're doing is multiplying. So we're looking at just relative heights of temperature. Now if we look here at the next one, you try it. This is 4 and this is 4. So what is that? This would be 16. We go here. You're kind of getting the point now, right? 5 and 3. Back down to 15. And then we have 6 and 2. We have 12. 12 units of temperature, right? So what's important to know here is that these 2 points right here, so if we were to connect these dots, sorry, see if I can get that right. See where it's 15 and 15? If we were to connect A and C and really not skip B, we skip B because they're not the same, but A and C, all the points along this line skipping B, if I were to make a perfect curve, maybe something like that, would be something called isothermal. Right? And maybe I have a better picture of that on the next one. Isothermal. Iso means the same, and what does thermal mean, do you think? It's temperature, same temperature. So let's look at another graph here. All right, if we do work or add heat to the trapped gas, you would change the pressure volume. Which change of pressure volume would cause the gas to get warmer? All right, so let's look at work equals pressure times change in volume, and also temperature equals pressure by volume. Okay, so if we are moving in this direction here, this is negative volume increase, so that means we're compressing it. So if we are compressing the volume, right, this would be work done to the system, right? But it could mean that it's decreasing because the temperature is decreasing, right? So if you just imagine, like if you cool down a gas, what does it do? It condenses, right? And when it condenses, the volume is going to decrease, right? It's going to have a negative change in volume. All right, if you're increasing, so from here to here, if you're increasing the volume, but you are keeping the pressure the same, right? That means the temperature has to go up, right? Because you are increasing the volume, so what's going to happen to temperature? It has to go up, right? If you increase the pressure, so we're assuming we're keeping everything the same, right? Except for one thing, we're changing one variable at a time. So if I go and change the pressure, if I increase the pressure here, at A, if I increase the pressure, but I keep the volume the same, well, you can just imagine if you were inside like a room with kids and then I made the walls compress inward, right? If I made the walls kind of like squeeze together, if I made the walls squeeze together like that, everybody in the room would get pretty uncomfortable really quickly, right? It would feel like it gets a lot hotter, right? So that would be kind of an example of that, right? So just kind of look at these graphs and evaluate that. All right, second law, heat flows from hot to cold. And this is entropy. Heat flows from the hot to cold. That is a law. It's not going to go the other. It's not going to go cold to hot naturally. Okay, you have to add force or work to the system to do that. And the reason for that is kind of imagine that if I were to get like a Jenga castle, right, or maybe like a block of Legos, and kick it over, it could fall down. It could fall down all over the place, right? It could fall down all over the place. It might fall here, 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 here. It might end up getting like a just big mess of things all over the floor. Like perhaps this is something you might see after you kick over a bunch of Legos, right? But what you would not expect if I kicked it for this pile of garbage here, this pile of Legos, you would not expect it to ever go back on its own and reconstruct itself into a nice tower, right? That's just something that's almost statistically impossible, right? You would not expect this to happen. This is very similar to why things travel from hot to cold. It's entropy. It's so statistically probable that it will go into higher levels of disorder and disorganization that it is a law, right? We call it the law of the second law of thermodynamics, the law of entropy. Okay, that's just the way it's going. And in fact, this is kind of the really sad thing about the universe, is that the universe is always increasing in entropy. And if you remember from your chemistry class, this is S, right? Delta S, entropy. All right? So we will only become more disordered over time. Energy will not be organized, right? So if you can imagine like something like a block of ice, right? A block of ice melts, right? So that's disorganizing that nice ordered, hexagonal molecular structured ice cubes, and then eventually it'll evaporate. And that's higher levels of disorder, right? And that's how the universe is going. We're losing order. Okay? And that has some very serious ramifications for the end game of the universe. Okay? The quality of energy is lowered with each transformation. So you can restate the second. Oh, here it is. Natural systems proceed in a state of disorder. Okay? Disordered energy you can only get it back to order if you put work into the system. So you have to work really hard to get that evaporated water to condense back down. And you're like, well, Mr. Bayona, I see rain clouds. It's condensing back into a liquid. That's more order, isn't it? And then even then, water freezes. So what does that mean? Well, if you are freezing liquid water, so you have like liquid water all over, and then this becomes like a nice ice cube, well, that means from here to here, what had to happen? The Q had to be negative. It had to leave the system. So you can only get more order in a system if the surrounding system increases in entropy. Okay, increases in entropy if it becomes more disordered. So you can't win. You can't. All right. And this is an idea of entropy. They usually show examples in a textbook of like a farm or something that's left to its own devices over time that'll just break down. Bridges do the exact same thing. That's why you have to upkeep them every year, right? You have to, if you just left bridges alone, after about 10 years, a lot of them would start cracking and falling. It's crazy, right? It's just entropy. It's just everything moving towards disorder. So just think about this. Imagine like you explode some gasoline in your engine. There's a lot of heat that was added to your engine block in order to do work to compress a piston, to change the volume, to change the temperature, right? But as that, expelled heat leaves the tailpipe, it's, that heat is useless. You're not going to be able to really do anything with it anymore. You can devise ways to get that heat to cycle back in, but you have to have some sort of heat in order to do work, right? And you have to give up some heat. So you have to have inefficiency in order to make things run. The addition of work in a system decreases entropy, right? And there's some ways that, especially the way that we generate electricity with coal plants and things like that, there are ways we can capture some of this escaped heat and vector it back into like a turbine or something and make it work again. All right, the third law, entropy of all systems at all states of a system is zero at absolute zero. So there's no entropy when you have something with no molecular motion at all. Everything is stopped, but this is not possible to reach. And we've gotten really, really, really close, but we haven't done this. Okay, the first law of thermodynamics, remember that law of thermodynamics can be restated as the internal energy is the Q plus the work, right? Plus or minus the work. So remember that this is done in joules, and joules is a form of what? Energy. And I'm telling you that if I get all the internal energy of a system, it either has to be heat or it's work done inside the system, right? Some sort of compression or force times a distance, right? So all of this here has to be accounted for. This 100% of whatever energy you put in on this side has to be equal to all this stuff over here. This has to be 100% as well. We're going to get into this mathematics in just a second. But this is basically what? If you were conserving joules on this side and joules on this side, what is that? It's the law of conservation of energy. So don't forget that. Okay, and we'll get into some mathematics today, and I'll probably put a Quest tutorial online for some of the harder problems. Okay?